In this last video on conservation momentum, we want to look at some more complicated cases of conservation momentum problems and problems that do not contain a given mass. Conservation momentum problems, because both kinetic and potential energy contain a mass variable, and as long as the mass is staying constant, mass can end up canceling out in the equation. You don't actually need to know the mass of the object to solve most conservation of momentum problems. So let's look at a bunch of examples here. With each of these examples, I would like you to break up your page. So if this is your page that you're taking your notes on, break up your page into two parts. Do your version of the problem on one side, then press play and take down any notes on how I did my version if it's different on your side. Then draw a line and do the next problem. And do that for each of the problems in this video to receive credit for your notes. First problem. A man can jump 2.2 meters high on Earth. If he goes to Jupiter, where the gravitational acceleration is 25 meters per second squared, how high would he jump? So press pause here, try it on your own, then press play, and on the right-hand side, record my answer if it's different from yours. Okay, we've got two parts here. We've got the Earth, and we've got Jupiter. Change the color of this so it's a little bit easier to see. On Earth, 1/2 mv initial squared plus mgh initial plus 1/2 mv final squared plus mg final. So I don't know the mass of this person, so I'm going to leave mass as m. The initial velocity of the person is what I'm trying to find. So I don't know how fast this person moved. I'm going to leave this as m. G is 9.81. The original height is 0. At the top of the jump, the velocity is 0. M times 9.81 times 2.2. So I get 1/2 mv initial squared equals 9.81 times 2.2 just 21.582 m. M's cancel. Divide by 1/2. I get 43. bi squared equals 43.164. Take the square root. I get 6.57. So that's the velocity that we're going to start with on the Earth, on Jupiter. Same idea. Now we can do the same equation. 1/2 mvi squared plus mghi equals 1/2 mv final squared plus mgh final. So 1/2 m times 6.57 squared plus m, g is now 25 times a height of 0 equals 1/2 m times 0 squared plus m times 25 times h final. So square 6.57, I get 43.164. Take 1/2 of that, I get 21.582 m equals m times 25 times hf. M's cancel. So I'm going to take 21.582 and divide by 25. I get 0.86 meters. So you take a person who could jump 2.2 meters, which is a very high height on Earth, almost a pretty much unrealistic height, and then you put that same person on Jupiter, they could only jump less than a meter. Okay, the next problem. Once again, press pause, try it on your own, and then press play and see my answer. So we have a roller coaster. This roller coaster is starting at the top of the first hill with a velocity of 3 meters per second. We want to know how fast it's going at the top of the next hill. So we're solving for V final here. So plug in our values. 1/2 m, V initial, 3 squared, m times 9.81 times 100 equals 1/2 m V final squared plus m times 9.81 times 2.5. So 3 squared is 9 times 1/2 is 4.5 times the mass plus 981 times the mass equals 1/2 mass V final squared. 9.81 times 2.5 is out to 24.525. Add 4 to 981. Subtract 24.525. I get 960.475 equals 1/2 m. It's 1/2 m V final squared. M's cancel. Divide by 1/2. Get 1920.95 equals V final squared. Take the square root. I get 43.83 meters per second for V final. Okay, the next problem. The same roller coaster goes through a tunnel that is 3 meters below ground level. So once again, I'm going to work with the same roller coaster. Doesn't matter which point I start with. I could start with the final point that I just solved for. I could start with the original point. I think it's easier and more effective to start with the original point because that's given data versus data you solve for and might have made a mistake. So our original velocity was 3. M times 9.81 times 100 equals 1/2 m V final squared plus m times 9.81. And now, because it's below ground, this height will be -3. So I get 4.5 m plus 981 m plus 1/2 mv final squared, -3 times 9.81, -29.43. So 981 plus 4.5, and we're going to add 29.43 m to both sides, meaning we'll get 1001.93 equals 1/2, that's m, equals 1/2 mv final squared. The m's cancel, divide by 1/2, 2029.86 equals v final squared. Take the square root, you get final velocity here of 45 meters per second. So now it's at a lower point. Instead of being at the previous problem at 2.5 meters, we're 3 meters below, and it's going even faster. More kinetic energy because there's less potential. One last problem. A 50-kilogram physics student is trying to develop a new amusement park ride. The student swings from 21 meters above the ground at rest. The bottom of the swing, 1 meter above the ground, the student lands in a 45-kilogram cart which slides forward 12 meters before stopping. The friction is the only force stopping the cart. What is the coefficient of kinetic friction? So this combines a lot of things that we have done earlier in the course. So we're going to start 1/2 mv initial squared, mgh initial. Make sure you've tried this on your own before watching my explanation. V final squared plus mgh final. So we're going to start and figure out how fast the cart is moving when it hits the person lands, how fast the person is moving when they land in the cart. So 1/2, 50, initial velocity, 0, plus m50 times 9.81 times 21 equals 1/2, 50, v final squared, plus 50 times 9.81 times the final height, which is 1 meter. 0, 50 times 9.81 times 21, $10,300.5 equals 25 v final squared. 50 times 9.81 times 1, which is 490.5. Subtract 490.5 from both sides. And we get 9810 equals 25 v final squared. Divide by 25. 392.4 equals v final squared. V final is 19.8 meters per second. So that tells us how fast the person's moving when they land in the cart. So let's move on to another screen to put some of this data down and solve the second half of this problem. In this case, we have an initial velocity, 19.8 meters per second, a final velocity of 0 meters per second. It's going to take 12 meters to come to a stop. The mass of the person in the cart combined is going to be 95 kilograms. The free body diagram will be force of gravity, force normal, and force friction. So we need to figure out the acceleration first. To figure out the acceleration, I think it's easiest to use Vf squared equals Vi squared 2a delta x. So 0 squared equals 19.8 squared plus 2 times a times 12. So 19.8 squared is out to 392.04 plus 24a minus 392.04 to both sides. The acceleration of this person would be negative 16.335 meters per second squared. Now we can use F net equals MA. F net equals 95 times negative 16.335. Meaning the net force would have to be 1,551.83 newtons, which is our force of friction here. Force of gravity, the 95 times 9.81, comes out to 931.95 newtons. Since it's not accelerating up or down, the force normal will be the same value. Now we remember force friction equals coefficient of friction times force normal. So the net force here was the force friction. We're trying to solve for the coefficient of friction. This is 931.95. Divide, and our coefficient comes out to 1.67, which is an unreasonably large coefficient, but this is how we would go about solving that problem. So this is a much more complicated, puts a lot of things together that we've been covering through the semester.